Section 2.6 has to do with least common multiple. And so you're going to see it written as LCM. And so it's going to be the smallest common multiple. Remember, multiple means count by. So if we're doing the least common multiple of, say, 4 and 6, we're going to be counting by 4s and counting by 6s to see which is the first number they both have in common. So 4, 8, 12, 16, and 6, 12, 18, 24, and all of these, of course, can go on forever. So what is the first number that they both have that's exactly the same? Well, we notice that they're both 12. It's the first number that they both have on the list that's the same number. So the LCM of 4 and 6 is 12. Another way we could do this is if we take a look at these numbers again and we check, first off, does 4 go into 6? No. And I always take the smaller number and put it into the bigger one. So our first multiple is not common. So we look at the next multiple. Does 4 go into 12? Yes. So that's another way to do the same thing that we did up above by writing all the numbers out. Either way is fine, either way works. And there's a third way I'm going to show you here in just a minute, but I want to get these two methods down first. So let's say we're going to do the least common multiple about 3 and 15. So we're counting by 3s and counting by 15s. So our first check is, does 3 go into 15? Yes. Therefore, our least common multiple then is 15 because the smaller number went into the bigger number. So let's say that we had 3 and, let's see, how about 10? So we're counting by 3s, we're counting by 10s. So does 3 go into 10? No. So what's the next multiple of 10? 20. Does 3 go into 20? No. What's our next multiple? 30. Does 3 go into 30? Yes. So we could have written 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. We could have done that. Or we just start checking the larger multiple and seeing if the smaller number will go into that number as a factor of. So a couple of different methods. So let's do one more here with some bigger numbers. So let's say that we had 3 numbers. We had 3, 4, and 9. Okay? So I always then use the second biggest number and get a common multiple with the larger number. So does 4 go into 9? No. Next multiple is 18. Does 4 go into 18? No. Next multiple is 27. Does 4 go into 27? No. Next multiple is 36. Does 4 go into 36? Yes. So we now know that 4 and 9 have a common multiple of 36. But we have one more number to check. Does 3 go into 36? Yes. So now we know that this is the least common multiple. It's the first number that's going to be the same on all the lists. We could have written the 4 out, 4, 8, 12, 16, 20, and so on, until we got to 36. And we could have done 3, 6, 9, 12, 15. You see how that's a lot more work to just simply check. Writing them out is a lot more work than just simply checking. So that's why I advise this particular method. There's also another method to work with some larger numbers. So let's say that we are going to do, in the book example, problem number 24. They're going to do the least common multiple between 22 and 33. Well, the numbers are a little bigger than these, and they're a little closer together. It means it's probably going to be a fairly large number in our answer. So we could do it a couple of different ways. So we can count by 33s. So 33 and 33 is 66. Does 22 go into 66? Well, yes, it does. So that one wasn't bad, but you wouldn't know it for sure by looking at it. So I'm going to introduce my third method we talked about. So we know what the answer is. We know it's 66. But let's do this by prime factor method. So we're going to prime factor both of these numbers into prime factors. So 22 is going to be 2 times 11, and this is going to be 3 times 11. Okay, so we're going to write this out in this form. 2 to the first times 11 to the first, because there's one of both of these. And 33 is going to be 3 to the first times 11 to the first. So when we're doing the least common multiple method using prime factorizations, we go through and we look for every number that's on any of the rows. So I notice I have a 2's, I have 3's, and I have 11's. So then I go through and I find the biggest exponent attached to any of the numbers. So I have 2 to the first. I don't have any 2's down here, so that's just the one I'm going to use. So I put 2 to the first in my answer. Then I notice I have 3 here. Don't have 3's anywhere else, so 3 goes into my answer. And then I have 11 to the first and 11 to the first down here. So it's the same. I just need one. I just need the one with the biggest exponent. If it's the same, I just simply write it down. So now I have 2 to the first, which is 2, 3 to the first is 3, 11 to the first is 11, and I just simply multiply that. 2 times 3 is 6 times 11 is 66. And that's another way to do the same type of thing. So let's say that we had some bigger numbers here. Let's have 20, 25, and 30. Okay? We could do it a couple of different ways. We could write these all out, 20, 40, 60, and so on, and 25, 50, 75, 100, and so on. Or we can do it the prime factorization method. So let's prime factor 20 first. So that's going to be a 4 and a 5, and a 2 and a 2. 25 is going to be 5 and 5. And 30 is going to be 5's prime, 6 is not, it's a tree. So when we write these out, we have 2 squared, because I have 2 times 5 to the first. Here I have 5 squared, and here I have 1, 2, 1, 3, should probably circle those, huh? Otherwise circle the 6, times 5 to the first. All right? So in our answer then, we have 2's, 3's, and 5's. So we're looking, we have 2's here, we have 2's here. Which one has the biggest exponent? Right here for the 20, 2 squared. So that's the one that goes in my answer. I have 3's here, but I don't have 3's anywhere else, so the biggest 3 is 3 to the first. I have 5's here, 5's here, 5's here. So our biggest exponent, remember, is the one that's used, and that's 5 squared. So now I'm going to convert these back. 2 squared is 4. 3 to the first, of course, is 3, and 5 squared is 25. So 3 times 25 is 75, times 4 then is going to be 300. And that is going to be our least common multiple. Now that would have been kind of hard to do with this method. I mean, our rows would have gotten pretty long. It takes a little bit of time, but it's not too bad to do the prime factorization method, especially when you have multiple numbered and they're fairly large. Okay, let's do one more example of that. So let's do another 3-number one. This is problem number 33 in the textbook. 9, 12, and 15. So if we do our prime factorization of 9, that's going to be 3 and 3. So that's going to be 3 squared. Okay, our prime factorization of 12, we have 4 and 3. 3 is prime, gets a circle, 4 is not, gets a branch, 2 and 2. So we're going to have 2 squared times 3. And our last one is 15, and 3 times 5. All right? So we have 2's, 3's, and 5's. So this is 1. These are all to the first. So our biggest 2 is right here. It's our only 2. So part of our answer then is going to be 2 squared, because it's our only 2 and it has the biggest exponent. We have 3's here, 3's here, 3's here. Our biggest one is right here. It's 3 squared. And then 5, the only place we have a 5 is right there, so that's part of the answer, 5 to the first. We convert it back into its original number. 2 squared is 4. 3 squared is 9. 3 times 3, remember? And 5 squared is, 5 to the first is 5. So now we have 36 times 5 is going to give us a total of 180, and that is our least common multiple. Again, you could have done it any of these other methods. You could have written 15, done the 9, the 12, the 15, 15, 30, 45, and then check each one of those until you find a multiple of 12, or probably with multiple numbers, and as they continue to get bigger, I would highly recommend doing the prime factorization method. Good luck with the homework.